Today, on How It's Made. Wood-burning stoves. We're getting all fired up to bring you this story. Orthoses. Brace yourself for an inside look at these limb supports. Ballet slippers. The whole song and dance. And buses. We'll check out every stop on the production line. Wood-burning stoves do more than create a cozy ambiance. They're also powerful enough to heat an entire house. More and more people are installing a wood stove as an additional heat source in their home. It's economical, and the new low-emission models are more environmentally friendly. Every wood stove has a fire baffle, a stainless steel barrier above the burning wood that shields the top from the intense heat. The baffle also slows down the smoke exiting by the chimney, which reduces the upward draft that the rising heat creates. Production begins with large steel sheets that are 8 millimeters thick. A computer-guided laser cuts out pieces that workers will shape into the various parts of the stove. The laser slices through the metal quickly and with extreme precision. And because it cuts with intense light rather than punching force, the pieces have neat, smooth edges. Workers use a strong magnet to lift and transfer the pieces to the next production area. The largest piece becomes the surround, the part that forms the sides and back of the wood stove. Workers use a machine called a press brake to shape it. A computer guides this large hydraulic press to bend the flat steel in exactly the right spots. Now they position the surround in an assembly jig to keep it steady during welding. After welding the front of the stove to the surround, they weld the air intake, which allows oxygen to enter the stove and feed the fire. Next, they weld the top, the fire baffle, and air channels near the top, which are also designed to feed the fire with oxygen. The quality of welding in a wood stove is critical because the joints have to be able to withstand extreme heat. Now they weld the bottom of the stove. It has a hole in the middle through which you sweep the embers to an ash pan below. Now they weld the flue collar, the steel ring that attaches the stove to the flue pipe that leads to the chimney. Workers now bolt the stove to a pedestal. The pedestal is also made of welded steel. Meanwhile, the door takes shape. They glue a fiberglass rope to the perimeter of the door frame using a silicone-based glue that's resistant to extreme temperatures. This cord prevents air from seeping in through the door and fueling the fire out of control. After installing the locking door handle, they weld the door hinges. The stove's interior, where the wood burns, is known as the combustion chamber. They line it with bricks to protect the walls from warping in the intense heat. Bricks do deteriorate over time, but it's easy to replace them. The last steel part they install is the cap for the ash pan. Now an automated conveyor transfers the stove to the paint station, where a robotic arm sprays on a coat of heat-resistant paint. Once the paint air dries, a worker removes the door to install its glass panel. This isn't your run-of-the-mill window glass. It contains ceramic, which enables it to withstand temperatures up to 1090 degrees Celsius. With the glass panel in place, workers can apply decorative features and information stickers. Then, they put the door back on and lock it shut. They rivet on the company logo. Then install a fan in the back. The fan blows out the heat that the stove generates. When the wood-burning stove leaves the factory, its coat of paint is dry but not yet cured. The heat cures it when you fire up your stove for the first time. Orthoses are devices such as arch supports and braces that address a joint or muscle problem in the back or extremities. An orthosis can provide artificial support, prevent or correct a deformity, or improve how a weak or painful area functions. You can buy an orthosis off the shelf or have one custom made. Producing a custom-made orthosis starts with a thorough examination. A certified professional, called an orthotist, analyzes the problem area. In the case of this patient, the feet. After a few manual manipulations to test the range of motion and pinpoint weakness or pain, the orthotist uses various instruments to measure the angles of the different parts of the feet. Then, it's on to specialized devices that analyze foot position and movement during standing and walking, and how body weight is distributed onto the feet. In this scan, the red areas show that more weight is landing on the left foot than on the right. Next, a 3D impression in foam. It goes to the production department, where technicians fill it with plaster. Once it dries, they extract an exact model of both feet. Now they can construct the orthosis piece by piece. Most of the components are made of different types of polyurethane, a lightweight thermoplastic. Each type is designed to produce a specific effect at a different phase of the patient's footstep. For example, the blue base is made of rigid polyurethane that holds the foot in the correct position. At the front, dense black polyurethane helps propulsion and reduces stress on that side of the foot. They cover the assembled orthosis with a sheet of glue and put it into a vacuum press. The press applies heat to activate the adhesive. It sucks out the air between the components and compresses them tightly together. When the orthosis comes out, they place it on the model of the corresponding foot. Then it goes into a different vacuum press to mold it to the shape. They add made-to-measure corrective parts in latex foam. Then, using hypoallergenic glue, line the orthosis with a soft polyurethane. All that's left to do now is buff the orthosis. This smooths all the surfaces. To ensure the orthosis delivers the goods, the patient redoes the key tests while wearing it. Remember that scan showing red areas? They're gone now because the patient's feet now bear her body weight equally. This patient has arrived with a doctor's prescription for a knee brace. The orthotist analyzes his mobility, flexion, and balance, then sends the technical specifications to the production department. There, technicians make a model of the leg. They begin by positioning the leg at a 12-degree angle and wrapping it in plaster bandages. While waiting for the fast-set plaster to harden, the patient chooses a decorative pattern for the outside of the brace. The hardened cast serves as a mold. Technicians pour in plaster, let it harden, then remove the cast. After smoothing the surface, they draw technical markings, then install the lightweight aluminum joints that'll enable the orthosis to bend. Now they run a sheet of plastic through an oven. This is high-memory plastic, meaning that when you form it, it remembers the shape and maintains it. The design the patient chose comes printed on transfer paper. They use a laser thermometer to ensure the plastic is at the perfect temperature for the pigments to penetrate properly. They carefully position the hot decorative plastic on the model. Using a vacuum bag, they remove the air and press the plastic on tightly. The plastic sets in about 2 minutes, maintaining the form. They cut the required shape, line the inside, and sand the edges smooth. Finally, they attach straps to fasten the orthoses to the leg. The orthotist checks the fit on the patient, then runs various tests to make sure the orthosis is doing exactly what it's designed to do. Ever wonder how ballerinas manage to dance on the tips of their toes? It takes years of training, remarkable skill, and special ballet slippers. These toe shoes are handmade in what's truly a manufacturing pas de deux, a graceful pairing of traditional methods and modern materials. They sew the toe shoe's exterior from 3 pieces of satin. They cut those pieces using a press equipped with a metal die. It slices through enough fabric at a time to make 4 pairs of shoes. They also cut a pure cotton lining for each piece to protect the dancer's feet from irritation. This V-shaped piece is called the vamp. It'll become the front half of the shoe. The seamstress extends the V by attaching the 2 other satin pieces called the quarter panels. They'll form the back half of the shoe. She sews the ends of the V together, making a heel seam, which she reinforces with a rayon ribbon. Then she feeds the same type of ribbon through a special machine that folds it in half over a drawstring. She stitches it to the top perimeter of the shoe. This encased drawstring will enable the dancer to pull the shoe tightly around her foot. Now they put the satin upper onto a wooden form to check the sizing. It's absolutely critical that the height of the vamp be correct to within 3 millimeters. If it's even slightly off, the top of the shoe will cut into the dancer's foot. The shoemaker nails the cotton lining to an insole on the bottom of the form. The insole is made of rigid cardboard for support, imbued with plastic for flexibility. After trimming off the excess, he glues the lining onto the insole, making neat little pleats. Once the glue dries, he removes the nail and trims the excess pleating to eliminate any bumps that would irritate the foot. Now they sculpt the toe box, the hard encasing inside the tip of the shoe. It's made of papier mâché, only instead of paper and paste, they use fabric and paste. Then they soften up a piece of resin-coated cotton in water and apply it on top. Next, they saturate 2 pieces of burlap with paste and apply them one after the other over the cotton. The paste is made of flour, water, starches, and a rubber and plastic-based resin that hardens to a semi-flexible state. That's key because the toe box has to be stiff enough to bear the dancer's full weight, yet flexible enough so that the ballerina can move fluidly. Now the final layer of fabric, a piece of pure cotton. They wrap the toe box in plastic wrap to keep the hammer clean as they square off the front, creating what's known as the platform. Then they press the toe box onto a piece of marble to make it completely flat. They verify that the platform is perfectly square. If not, the ballerina will topple over. After letting the toe box dry for 24 hours, they glue the lining over it with contact cement. They trim off the excess, then glue the satin over the lining, forming delicate pleats. They use lighter glue this time because contact cement would stain the fabric. They apply a foam filler to even out the shoe's underside, then coat it with high-strength vinyl glue. They apply the same glue to a sole, then leave both to air dry. 24 hours later, they put them on a heater set to 93 degrees Celsius. This reactivates the dried glue in about half a minute. They apply the sole, then put the shoe in a press for 15 seconds to solidify the bond. Now they can remove the shoe from the form. The sole is made of suede, a material that has just the right amount of grip. It's non-slip, yet still enables the dancer to glide smoothly across the floor. The last step is to glue in a white suede sock liner. It cushions the ballerina's foot and keeps it from slipping forward when she's dancing on her toes. A city's fleet of public transit vehicles might include standard buses, low-floor buses, or both. Low-floor buses have a special kneeling feature. When they pull up to the bus stop, they can mechanically lower themselves to curb height to make boarding easier for children, senior citizens, and handicapped people. This low-floor bus is 12.2 meters long and can carry more than 80 passengers. To build the bus's internal structure, workers put stainless steel bars into a press. It applies between 80 and 100 tons of pressure, bending them to the required shape. Workers assemble the structural pieces on a support frame called an assembly jig. They use an electronic inspection arm to verify their work. Once they've assembled the roof structure and the side structures, they bring them together for welding. Everything goes on a rotating jig. It turns like a giant rotisserie, giving workers easy access to whatever part of the bus they need to weld. When the welding is finished, they turn the bus right side up. They put the structure on a dolly and release it from the jig so that they can move it down the production line. Meanwhile, the stainless steel structure for the floor of the bus takes shape. Once that's complete, it's back onto the rotating assembly jig to weld it to the rest of the structure. This bus factory uses stainless steel because it stands up well to corrosion. Transit systems need to keep these buses running full-time for up to 20 years. Less rusting means fewer expensive and time-consuming repairs. Workers now move the completed structure to another part of the factory where they spray the underframe and lower section with a black anti-abrasion coating. This protects against the noise and damage that stones and other road debris cause when they hit the bottom of the bus. Next, workers apply high-strength glue to the floor structure and lay down a subfloor. Then they drive in screws for reinforcement. Now they turn the bus upside down to install 4 tanks of compressed air under the roof. 3 are for the brake systems, the 4th for the doors and other mechanisms. Melamine ceiling panels hide everything that's under the roof. Next, the engine's radiator goes in at the rear of the bus. Then workers turn the bus right side up again and lay down a waterproof vinyl floor covering that's specially designed to withstand heavy-duty transit use. They cover the sides and roof with fiberglass panels. To prevent corrosion, workers use glue rather than screws or rivets. Then they attach the fiberglass front of the bus to the rest. The bus's low-emission diesel engine arrives at the factory already assembled. Workers attach it to the transmission and drive shaft in the engine compartment. Buses without air conditioning have sliding windows that open widely. On air-conditioned buses, just a small top section opens. The upholstery on the molded fiberglass seats is a velour-like fabric woven onto a strong canvas, then glued onto a fiberglass insert. This construction makes it impossible for vandals to slash the seat with a knife. Workers install the driver's seat, the steering wheel, and all the controls, including the toggle switch that activates the kneeling feature. This bus also has a ramp for wheelchairs. A safety system locks the accelerator pedal and applies the brakes to prevent the bus from moving when the ramp or kneeling features are in operation. The finished bus undergoes a half-hour water infiltration test with all the systems running. This ensures there are no leaks. At every phase of production, the factory does a quality control inspection, checking everything from mechanical safety to finishings, right down to the tiniest of details. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.